Okay, so I asked you guys to get properties. I hope you got those. I'm going to pull that up there so you can see those. I know my writing's a little bit small there. I've written out how I did my interpolation between the temperatures, and because I forgot to write this down, remember we got to find T2. That was one of the things that the problem was asking for. So I had to write out interpolation for the temperature as well as H. Found values there. I've got H2 because S1 was 0.94202. I find that value between at 900 kilopascals, right? That value is between the values at 40 and 50. Right? So I've got to interpolate because that's 94202 falls between 9328 and 9661. The values at 50 and 40. So I've got to interpolate both H2 and T2 between those two. Okay, now, all right, we're done, right? That's what we got to do. No, we're not done. This is an engineering problem. It's multiple steps. It's complex, and there's a lot of algebra units involved, and that's okay. That's just how it is. What are we looking for? We're looking for the power input, the minimum power input. Okay, so we're going to find power where entropy generated is 0. That comes out in the second law that tells us the entropy is constant because it's adiabatic and reversible. So, what do I need to find this power input? Well, again, that comes from the first law. So I think we've got everything now. We need to solve the first law for the power input. The power input is equal to the mass flow rate times H2 minus H1. I've got now H2 and I've got H1 now. I don't have m dot yet. That's okay. We can find that. I've got enough information to find m dot. The power input is going to be m dot, which is going to be this 2 cubic meters for every minute divided by 0.12355 meters cubed per kilogram. And I get this question a lot of times about, Steve, do we have to write units in our calculations? No, you don't. You don't have to write units in your calculations. You just have to make sure the units work out at the end. So if all I've written here is 2 over this number, I'm not going to realize that this is kilograms per minute, which is not kilograms per second, so I'm not going to get kilowatts. This is kilograms per minute, not kilograms per second. To get it to go to per second, to get rid of this minute here, I've got to multiply by 1 minute for every 60 seconds. Okay, then I'm going to get per second, and then the whole thing's going to come out. You can do that conversion right here in your given information if you like. That's okay. But this gives me m dot in kilograms per second now, and I can see that clearly because I've written my units out. Again, you don't have to. You're just going to save yourself a lot of time and or a lot of points. If you don't care, you're going to save yourself, if you don't care either way, then, well, you're going to lose a lot of points. If you care about your time and you care about getting the right answer, if you put your units in there, you're going to save yourself a lot of time finding your unit errors very quickly. All right, I digress. What else are we doing? We need H2 minus H1. Well, I've got values for H2. H2 is 277.12 is what I can calculate there. H1 is minus 241.14. Now, these are values out of the 9th edition of Changle and Bowles. If you're using a different edition of Changle and Bowles, you're probably going to get slightly different numbers. In fact, the solution that's in my PowerPoint slides is actually slightly different because the R134 models have been updated in newer editions. So just fair warning there. If you look at my PowerPoints, it's like, Steve, these numbers don't match your PowerPoint. They're pretty darn close. They're within 4 significant figures. So it's really nothing we're going to worry about. Okay, what else here? That's it. Find a number. Calculate. Run it through your calculator. If we're in class, you guys know to already have this number ready for me, and then we can move faster while I ramble about things that are important, but not necessarily directly on this problem. I don't have a glare. Okay, good. So that's m dot per minute divided by 60. That should be m dot per second. All right? Oh, that's right. I got my solution over here. Yes, that is m dot per second, 0.27 kilograms per second. multiply that by my change here of 277.12. That's my enthalpy at state 2 minus the enthalpy at state 1, 241.14. And again, those are the same units, so I just group the units outside, distributed or factored out the units there. So that would be the enthalpy change multiplied by m dot, and I should get about 9.7. That's what I've got there. I'm going to run that through because that's not matching what I've got in my PowerPoint slides. Let me make sure. I know the 0.27. I'm okay with that. Multiply by this change. 277.12 minus 241.14. Okay. Now, if you're getting something different, leave it in the comments. Could be I've written something down incorrectly here. That appears to be what we're getting here, and that's okay. It's slightly different than what I had in my PowerPoint slides, but we're pretty darn close. Okay. If you have questions, let me know. And how are we on time? Oh, we got 8 minutes. Let's continue on. Okay. Alright, I'm pulling my PowerPoint slides up. I've got solutions here to that problem. And it's going to take my tablet just a second to catch up here. I apologize. There we go. Okay. So, nice example problem. L18, this is page 4. Okay. Set your side. Go to sleep for a moment. Alright. Ew, yuck. Glare, I apologize. There we go. Alright, entropy and temperature. If the process is reversible, remember the second law says, in its purest, rawest form, that an entropy change is going to be greater than the heat divided by temperature. If the process is reversible, it's an equal to. The entropy change is equal to heat divided by temperature. If I move this differential equation now around just a little bit, if I just move temperature over to the other side of the equation, that is dq is equal to the temperature times ds. And if I integrate both sides of this equation for process from state 1 to 2, assuming the process is reversible, the heat is equal to the integral of temperature with respect to entropy. Cool, that's kind of neat. What does that mean? Well, that means if I plot temperature with respect to entropy on a diagram, TS diagram. On a TS diagram, the area underneath the curve to get from state 1 to state 2, the area underneath that curve represents the heat transfer that's occurring. Again, if it's a reversible process. If it's not a reversible process, it's a little bit different. But, again, the integral of temperature with respect to entropy is equal to heat, okay? Which is kind of like boundary work, where the integral of pressure with respect to volume, one property with respect to another, is equal to the work. The integral of pressure with respect to volume is the work done by the system. The integral of temperature with respect to entropy is the heat absorbed by the system. That's kind of neat. Also kind of neat is when we first introduced the concept of entropy, and we said, well, historically it's a view of the entropy or the chaos or disorder or the unpredictableness of the system. For us as engineers, what it actually represents is the potential work that can be done, right, or the potential work that's required, versus the irreversibilities, the change in entropy. I plot H with respect to S. The change in enthalpy represents the work. The change in S represents the irreversibilities. Why the change? What, Steve? Why does the change in H represent the work? Oh, yeah. Control volume of the first law, that makes sense, right? This is the compressor. This is the first law equation. in the previous problem we just solved for the compressor, where the work or the power input is represented by the enthalpy change. Okay. All right, so these diagrams in your text, I'd like to take a minute or two, talk about them, and bring those up, and it also comes up a little bit when we derive the Gibbs equation here in just a little bit. Okay, so determining delta S. So we talk about that. Okay, there's three ways we can determine delta S. Why is this important? Well, look at the second law equation. And when you look at the second law equation, you can kind of look at it and say, well, there are three ways to determine delta S. Again, why is that important? Well, if you look at the second law equation, delta S is based off of heat transfer and entropy generated. Okay? So how do I find delta S? And then I can just focus on these other two quantities. Or how can I... That's one less thing to kind of demystify. How can I determine delta S? I've got to be able to quantify all those terms in that equation to use it. How can I use this equation? Well, let's get a handle on how do we determine delta S. There are three ways. The first way is we have tables. You have tables. 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 You have tables. For water... In our text, we have water and R134A. In some other texts, you might have ammonia, you might have propane, you might have R22 in some older texts, or R12 in some really old texts. You might have R410 in a lot of modern texts. You might even have carbon dioxide, where there's some experiments using that as a refrigerant. So you can have different substances. Our text, we have tables for water and R134, so if you learn how to use those, you can learn how to use any property tables. For, as we've seen before, you need two properties. If I get two properties, then I can determine S and all the other properties. If I need two properties for the water R134 at a particular state, then I can use these tables. For ideal gases, important. They give you this S degree value. S degree is not S. I cannot stress that to you enough. The ideal gas tables, when you look at those, they will give you, now they'll give you U and H for ideal gases, and you can use those. They will give you an S degree value. We can use it for something else, but we can't use it for S. We can't just take that S degree value for the ideal gas tables and plug it right into these S values. Okay? Now, we can use it for something else, and we'll talk about that later, but we're not quite there yet. Okay? So tables, first thing is, if it's water R134, we're going to use tables. We can go look up S values given two properties. Second thing, what I like to call the second law itself. Okay? The second law itself. What does that mean, Steve? Well, if you look at the second law, if I'm trying to determine delta S, that just means if I can quantify this right-hand side of the equation, that gives me delta S. Okay? So do I know something about the heat transfer and S generation? If it's adiabatic, that tells me that this integral of dq over t is equal to 0. Okay? If it's reversible, then that tells me the entropy generated is 0. Have they given me enough information that I can assume this process is reversible? Or does it just make sense to go ahead and assume the process is reversible and then figure out and use that as another property? All right, I'm going to have to start the next video there. Okay, so we'll be back in just a second.